We're very lucky today to have Dr. Rimpei Chiba. I'll keep the introduction short. Rimpei is a postdoc at CITA in Toronto, having done his PhD in theoretical physics at the University of Oxford with Ralph Heinrich. And before that, he was at the Tokyo Institute of Technology. He's probably the #1 expert in the world on the interaction between bars and galaxies and their surrounding dark matter halos, but is also interested in other dynamical things to do with galaxies, n-body simulations, and so on. And he's here for the rest of the week, and today he's going to tell us about how to probe dark matter using the bar in the Milky Way. So go ahead.
Okay, so thanks for the introduction, Chris. Okay, so today I want to talk about the work I did for my PhD thesis, and it's also the work that I'm continuing at CITA. Okay, so the background image that you're seeing here is a typical image of a barred galaxy. This one's called NG31298. The galactic bar is this linear stellar structure that is extending across the galactic center. And these galactic bars are observed in more than half of these galaxies in the local universe. So it's natural to ask whether our galaxy, our Milky Way, also has one of these bars or not. Now, obviously, we can't see our galaxy like this from a place-on view because we live inside a disk. But if we view our galaxy edge-on from inside, this is what we get. Okay. So you can see that we clearly see this asymmetric distribution of stars, which is exactly what we expect if one end of the bar is close to us and the other end is far away from us. And this measurement also tells us that the solar system exists somewhere around here, around 30 degrees away from the bar's major axis. And we also have evidence of bar from the stellar kinematics and also from gas kinematics. So all this evidence combined, we now believe beyond a reasonable doubt that the Milky Way is a typical barred galaxy. And my research is about using this galactic bar in our Milky Way to probe the surrounding dark matter. Okay, so first let me describe why we need a new approach to probe dark matter. Okay, so as you all know, the existence of dark matter has been implied from several observations. Here I'm just listing a few of them. The problem that I want to raise here is that most of the implications of dark matter that we have so far only measures the gravitational mass of dark matter. Gravitational mass in the sense that we are only detecting some anomalies in the gravitational potential that cannot be described by the Newtonian gravity of the baryons alone. But the fundamental problem of this is that any anomalies in the gravitational potential can in principle be explained by modifying the laws of gravity. Now, whether we can do this in a convincing way or not is a different question. But in principle, it's always possible because wherever we expect dark matter, we always find some amount of baryons there. Now, in contrast, galactic bars can be used to measure the inertial mass of dark matter. Now, of course, gravitational mass and inertial mass, they're the same thing. We know that they take the same value, but conceptually, they are two different things. Right? Gravitational mass basically quantifies the strength of gravity that the mass generates, whereas inertial mass quantifies how much matter gets accelerated when any kind of force is applied to it. And the reason why galactic bars can measure the inertial mass of dark matter is because galactic bars, when they're rotating, because they are non-axisymmetric structures, they torque the surrounding dark matter, right? And this torque will make the dark matter accelerate. And this acceleration of dark matter is a measure of the inertial mass. Now, obviously, we cannot measure the acceleration of dark matter, but from the conservation of energy and momentum, if dark matter is accelerating, if it's gaining angular momentum, then the bar must be decelerating, it must be spinning down. And this spin down of the bar is something that we could in principle infer, and this I will explain later how we can actually do this. So here, let me just make my point clear that the spin down of the galactic bar is a unique signal that we would expect only if dark matter exists. Okay, so here I'm just showing the result of our n-body simulations. The left plot shows the case where the bar is evolved inside a live dark matter, live in the sense that dark matter is moving and they're responding to the bar. So you can see that in this plot, the bar's rotational frequency as a function of time, you can see that the frequency is declining significantly from its initial value. On the other hand, if you don't assume any dark matter, and if you adapt MOND, you can see from this red curve here that the bar's pattern speed hardly changes, right? Because the bar doesn't have any opponent to exchange momentum and energy.
Doesn't the baryonic effect of baryonic friction increases in MOND?
It does a little bit, yes, okay. But only a little bit.
Not enough to count.
Yeah, yeah, exactly. Yeah.
Can we go back to your claim about the inertia
Yeah.
You're not measuring the acceleration, because I'm confused. You're not measuring the acceleration of the dark matter to a known force. You're just measuring the acceleration of the baryons of the bar. So to the force of gravity due to the dark matter, perhaps the exchange. So it's not the inertial mass, it's also the gravitational. In fact, yeah, is it really?
So I mean, the acceleration infers the inertia, it infers the existence of the inertial mass of dark matter.
But you're not measuring the acceleration of the dark matter, even you're measuring the acceleration.
So it's based on the assumption that the deceleration is caused by the acceleration of dark matter. So it's based on the assumption that those two are combined dynamically.
Yes, but if you were to make a model in which like what you are saying is that the inertial mass to gravitational mass is not one, some other constant for the dark matter, let's say. Would you even tell? Here you would just change slightly the amount of dark matter or something, and then everything would give you the same decay. I don't think this measurement constrains that ratio, does it? Really?
No, I'm not constraining the ratio between inertial mass and gravitational mass, right? Because this is confirmed experimentally, it's a high precision.
No, for the dark matter.
For the dark matter, yes. Or for the, wait, so you're saying that dark matter might have a different inertial
But
mass?
that's what you were saying. I don't buy any of these, but I mean, I just think everything's fine and Atlas PM is awesome. But you're saying that somehow you want to test you said the inertial mass of matter. I'm just getting confused.
Right, so it's just a conceptual. I'm just saying that these two are conceptually different. And gravitation, so for example, the gravitational part is an evidence that that comes from the galactic potential, and it measures the gravitational mass of dark matter.
If the dark matter had zero inertial mass, bar presumably wouldn't decelerate.
Right, yeah. So yeah, if it cannot absorb energy and momentum from the baryons, then of course,
It absorbs energy and momentum by gravitational mass.
Yeah. I'm not sure.
right,
Photons don't have mass, but they still interact,
right.
even gravitation.
Okay, well,
So you need both. It's probably like a product of inertial mass and of gravitation. If either is zero, then there's no effect.
okay, maybe I should have phrased it differently. Yeah, but let me just proceed on my result. Okay. So what this result is basically just telling us that if we can find any evidence that the bar has been slowing down in the past, we can use that as an evidence for the existence of dark matter. And this is something that cannot be explained by MOND or any other modified gravity theories unless they are violating the conservation of energy in a very peculiar way. So how do we measure the bar slowdown? Obviously, the slowdown of the bar happens over a very long time scale, giga time scale, which means that of course we cannot measure it directly. So the only way to do this is to infer it, to find traces of the bar slowdown in the current snapshot of the stellar disk. So in my talk, I will present two evidence for the spin down of the Milky Way's bar. One is based on the kinematics of the stellar disk, and one is based on the metallicity of the stellar disk. Okay, so to understand how the slowing bar affects the stellar disk, I first need to understand how the slowing down of the bar impacts the motion of an individual star. Okay. So let me start by describing what an angular action variables are. So the left plot shows the orbit in a two-dimensional axisymmetric potential, so in the absence of the bar. So you can see that even in the absence of the bar, if we kind of look at the orbit in real space, the positions and velocities are kind of fluctuating in a not so simple manner. So this means that x and v are not the best coordinates to characterize orbits. And the dynamics becomes much more simple if you label these orbits using integrals of motions, and actions are just one of these, but they're special in the sense that they can be used as a canonical momentum. Okay, so in a two-dimensional axisymmetric potential, we have two actions. One is J phi, which is the angular momentum. This is the one that describes the size of the guiding radius. And the other one is the radial action, which basically describes the extent of radial motion around the guiding radius. And the coordinate that is conjugate to these actions are called angle variables. And theta phi describes the phase of the orbit, of the guiding orbit, and theta r describes the phase of the radial oscillation around the guiding orbit. So you can see that the orbit that looked but complicated in the real space becomes a simple straight line in angle space. So now I'm going to perturb this with a bar. So here in this slide, there's a lot of information. So let me describe this one by one. So on the left plot, I'm going to show you how the orbit behaves in the bar's rotating frame. So this gray ellipse is the bar is on the x-axis. And I've marked 3 circles, which are the 3 most important radius in the bar galaxy, which is the outer inner resonance, the corotation resonance, and the inner linear resonance. So the outer inner resonance, this is a resonance that occurs when the orbit completes 2 radial oscillations once it goes around the bar. So basically the radial frequency and the azimuthal frequency has a ratio of 1 and 2. The black solid line is the corotation resonance. So this is when NR is 0, so when omega phi is just directly coupling with omega p. And the inner circle is the inner linear resonance. This is similar to the outer linear resonance, but it's just that the orbit is going around the bar in another way. So in my talk, I will mostly focus on the corotation resonance, but all the dynamics that I will explain will be naturally extended to all our kind of resonances. Okay, so here's how it looks when the orbit evolves. So as you can see from this blue orbit, when the stars lie close to the corotation radius, it can become resonantly trapped. And when it becomes resonantly trapped, you can see that the phase is locked with respect to the bar. It goes back and forth the bar's minor axis. And the red orbit, in contrast, is untrapped, so it freely circulates around the bar. And if you look at these orbits in the action space, you can see that the actions are no longer conserved. And in particular, if you look at the trapped orbit, you can see that they are exhibiting this very long, slow oscillation around resonances. But even for these orbits, there are actions that are approximately conserved, which are the fast action and the libration action. The fast action is just simply a linear combination of old action, and it just basically describes where the orbit is trapped along the resonance line. And for example, for the corotation resonance, again, NR is 0. So fast action is just the radial action. And the other one, the libration action, is a quantity that describes the extent of the amplitude of motion around the resonance. Okay. And this is defined in the so-called slow angle action plane. So you can see that in this phase space, the trapped orbit is revolving around the resonance, and the untrapped orbit is circulating outside. And the libration action is defined as the phase space area enclosed by this orbit. So now I want to make the bar slow down, so I need a model for the bar's spin down. So here, for the bar's pattern speed, anybody's simulation actually shows that the pattern speed doesn't decline linearly, but its slowing rate actually reduces over time. And a good fit is given by a 1/t law. If I adapt this model, then the dimensionless slowing rate of the bar, which I defined as eta minus omega p dot over omega p squared, this dimensionless parameter becomes a constant. So I can very conveniently parameterize how fast the bar slows down with just one parameter. And then as the bar slows down, its corotation radius expands radially outward. Right? And at the same time, the bar grows in length. Okay? So I modeled the bar's potential such that its characteristic radial length increases in proportion to the corotation radius. So now using this model, I will make the bar slow down. So you can see that as the bar slows down, the corotation radius is expanding radially outwards. And as it does so, the orbits that are trapped in resonance are dragged along with the resonance. Okay? And the reason why they are dragged is because these actions are adiabatic invariant, which basically means that if the potential of the system evolves at a time scale longer than the fast period and the libration period, the orbit have to evolve in such a way that they conserve their actions approximately constant. So that's why they have to stay in one of these contours here. So this result already suggests that if the bar has been slowing down, then it would have caused a significant change in the distribution of stars.
Is the slowdown of the bar sufficiently slow that this adiabatic dragging of orbits is always applicable?
Yeah, so I will come back to the point. So actually, the final result will depend significantly on how fast the bar is going.
Okay.
So here I'm just again showing the image of the galaxy. The yellow point here marks the approximate position of the sun. And where we observe the stars near the sun, basically many stars pass near the sun at a variety of velocities depending on what kind of orbits they belong to. For example, if our orbit with a smaller guiding radius might visit us when they are close to its apocenter, whereas an orbit with a larger guiding radius might visit us near its pericenter. So even if we observe only stars close to the solar neighborhood, we actually get a lot of information about the entire galaxy. Okay, and we plot the distribution of stars near the sun in the velocity space. This is what we get. So the x-axis is the radial velocity, y-axis is the azimuthal velocity, and this was observed by the Gaia Space Telescope. So you can see that there's a lot of structures here. And our goal is to find if there's any features in this distribution that implies the bar slowdown. Now I'm going to compare the data with my model where I have a test particle simulation where I'm perturbing the stellar disk with a bar that is slowing down. Okay. So initially I set the pattern speed to 80, which is around roughly 2 times the current value. So as the bar slows down, the resonances of the bar sweeps through the solar neighborhood one by one. So this one was the 1-1 resonance. This one is the 1-2 resonance, outer ring resonance. And then the higher order resonances comes. And finally, the corotation resonances. All right.
How sensitive is it to your choice of initial condition? You're assuming an unperturbed spherical.
Yes. The thing is that initially when the pattern speed is high, the bar is also small and weak. So actually the effect there is actually quite small. So now I'm comparing 2 simulations where I, in this plot where I made the bar slow down, and in contrast here, I had a bar that is just rotating at a constant pattern speed. So you can see that even if the current parameter of the bar is exactly the same, whether the bar has been slowing down or not makes a significant difference. And in particular, if you look at the stars trapped in the corotation resonance, which is marked by this black curve, you can see that if the bar has been slowing down, then the corotation resonance would have existed initially at the inner disk, where the phase space density is higher. So it will capture stars at that dense region. And then as the bar slows down, the resonance will drag those dense fractured stars to the solar neighborhood. So it creates this bimodal structure, which we do not see in the case of a constant rotating bar. And this can naturally explain the so-called Hercules to the stream that we observed in the data. So this was my first kinematic implication of the bar's slowdown. As I've just said, the dynamics is significantly sensitive to how fast the bar slows down. So let me just describe the basic theory of what happens when a bar slows down.
Yeah, I'm sorry, in the previous figure, the previous slide. Have you realigned the panels, the observational and the sloping bar? Because I think it should depend on the orientation, right? Orientation of the sun with respect to the bar and all that.
The angle respects the bar.
Yeah.
Yes, of course, it will change depending on the angle of the bar. But most sensibly, it depends actually on the current pattern speed, because this is the value that really determines where the resonance is exactly.
Right, but since it's anisotropic, you have to know the. Okay, you assume the 30 degrees.
Exactly.
Okay.
So here is just a Hamiltonian of an orbit subject to a slowing bar. I won't go in detail, but you can see that it resembles a pendulum where we have a kinetic term and a potential term that depends on the angle sinusoidally. But you can see that it also has a term that is linear in the angle, and it has a coefficient S, which we call it the speed parameter. This is the parameter that describes the ratio between the vibration time and the time scale of the drift of the resonance. So when S is 0, this is the case where the bar is not slowing down. And in this case, the phase space looks very much like a pendulum. So the stars trapped in resonance vibrate, while the stars untrapped are circulating outside. But when the bar starts to slow down, when I increase the S, you can see that the potential gets linearly tilted because of this linear term. So the amount of stars that can trapped in resonance can contract. And if I increase the S more, you get more contract. Then at the critical point where S is larger than 1, the potential will no longer form a local minimum. which means that none of the orbit can stay trapped in resonance. So physically, this means that if the bar is slowing down too rapidly, then the resonance will sweep through the stars too rapidly, such that the stars won't be able to catch up with the resonance. And it's also the breakdown of the adiabaticity here. And
Are you assuming here that A is constant? The bar strength?
no, it's so, yeah, the thing is that, yeah, the speed parameter is actually the ratio between eta and A. Yeah. So I'm just changing S. So it really just depends on the ratio, not just A.
Sorry, but in each of these images, or a general assumption, you say eta is always constant, or you're assuming A is constant.
In my simulation, yes.
Do you also assume that A is constant?
Right, in my simulation, yes, A is also constant.
Is it reasonable to assume that if the bar is slowing, that the strength would be increasing though?
Yes, so from n-body simulations, we do see that A slightly increases, but maybe like a factor of like 1.2 or 1.5 over its lifetime. Yes, so as I just explained, in the epicycle approximation, which is valid when the orbit is close to the circular orbit, this S reduces to the ratio between these parameters, which is the parameter that I'm using to model my bar. So I did the simulation for a wide range of bar slowing rate and bar strengths. So this result shows that, as predicted by theory, if the bar strength is large and or if the bar slowing rate is small, then the speed parameter will be small, such that the solar neighborhood will be dominated by resonant stars. Whereas if the bar strength is too weak, or if the bar slowing rate is too large, then you can see that the trap region is too small, so that the resonant feature is going to be too weak. And both cases not matching the data. So which means that at a given bar strength, which we can constrain from other separate studies, there is an optimal bar slowing rate that matches the data. So I quantified the agreement between the data and the simulation, and then using the prior for the bar strength, which is constrained from a separate study using the inner gas kinematics, I estimated the bar slowing rate eta. And then on the right, I'm comparing this value with n-body simulations, which are particularly tailored to the Milky Way galaxy. So these two red points are the one that uses MOND and modified gravity. So these simulations predict a very small slowing rate, which is more than 2 sigma offset from my measurement. And these black data are the n-body simulations that assume the standard cold dark matter. And you can see that there is a lot of scatter depending on the numerical methods, the ancient conditions, whether the simulations have gas or not. But generally, my measurement is in more agreement with the cold dark matter than the MOND theories.
I have a naive question. You say n-body simulations tailored to the Milky Way galaxy. So what does that mean in practice?
So it means that the parameters are tailored to the Milky Way galaxy.
But like, so again, very naive question. What are these parameters? Like the
So
density of,
yeah, the mass of the galaxies and the scales, the ratings.
you have some potential that you put in. So, okay.
But do they also simulate the growth of the Milky Way mass?
Yeah.
How well we know that?
So actually, a lot of people actually don't model the growth of the simulation. So they actually start with a galaxy at the same size as the current galaxy.
Yeah, that
which
will be
is
problematic.
yeah, very unstable, and it quickly forms stars and so on. For example, this simulation by Alma Schoenhoff basically modeled the kind of growth, which was adjusted to the star formation rate.
How well do we know the distribution of dark matter in Milky Way?
We have a rough estimate on how the spatial distribution is, but we don't have any idea on what the kinematics are.
Yeah.
How did you get your measurement? You have this histogram from Gaia, and then you have your plots, but was this a quantitative comparison? Was it by how
Yes.
did you manage?
Yes, so that's a good question. So the thing is that the quantitative comparison depends on a lot of things, not just about slowing rate, not just about pattern speed, but also like on the velocity dispersion and so on. So I didn't want to fit everything, right? So I only fitted the regions in the corotating region here. And basically the main feature of here is basically the asymmetry of stars that have positive radial velocity or negative radial velocity. Quantified using the asymmetry in the radial velocity in the corotating region.
How complete is Gaia in this little patch of phase space?
In this particular, so these are the stars that are like in the solar neighborhood, like 300 Pascal over the sun. The selection function is almost complete. We have 100% measurements. Okay. Now, all the analysis that I showed you so far is based on the assumption that the Hercules stream was shaped by the corotation resonance of the bar. But the problem of this is that actually the Hercules stream can also be shaped by other perturbations in the galaxies, like the spiral arms or the impact by the merging satellite. So by just looking at the kinematics of the Hercules, it was difficult to conclude whether the bar has really been slowing down or not. So I decided to look into the metallicity of stars because metallicity directly indicate where the stars come from. So here I'm showing the metallicity of gas as a function of radius. So you can see that the metallicity has a negative gradient in radius, which means that basically stars that were born at the inner disk are more metal-rich. So I colored the local velocity space with mean metallicity, and now we can see that the Hercules stream is significantly metal-rich, which indicate that these stars come from the inner galaxy. And yes, this is exactly what we expect if the bar has been slowed down. But the thing is that the fact that the Hercules stream is metal-rich is not a new finding. This was already known as early as 1970s. The new thing that we can do now from using the Gaia data is that we can actually model the detailed metallicity distribution within the resonance, not just when compared with outside. So to understand how
there's also some red outside of your line. What's that? Or is that?
These guys.
Yeah.
So these are known open clusters. It's like the Haddas clusters. So actually, some people might think that this might also be an open cluster. But if you look at the distribution in age, it has a broad distribution. So that's why this is probably not an open cluster, whereas the open clusters clearly have a monotonic age distribution. So to understand how the metallicity is distributed within the resonance, I first need to understand how the resonance gets populated by the stars. Okay, so in that simulation, I will show how the resonance evolves as it sweeps through the disk. So the resonance is sweeping upward, so the y-axis is moving down. And you can see that as the resonance moves up, the amplitude is increasing as we continuously capture the surrounding orbit. And once these orbits get captured in, they conserve the action of vibration, which basically characterizes this distance to the resonance center. So you can see that the order of capturing is preserved inside the resonance. The red orbit, which were captured earlier, they occupy the core of the resonance, whereas these blue orbits, which occupy the surface of the resonance, they are the one that was captured recently. So the phase space evolves just like a tree ring. So in the tree ring, a new ring always appears at the bark. It's not from the center, it appears at the bark. And then every year it records the climate condition of that. For example, if the amount of rain changed, or if there was a forest fire, those changes in event will be all recorded. And a similar thing happens to the phase space of the bar's resonances, because stars can only enter the resonance from the surface. And once it enters, it conserves action vibrations, these concentric rings. So we can use the distance to the resonance center as a kind of chronometer to infer the bar's evolutionary history. And in particular, if the bar has been slowed down, then stars captured earlier at the inner disk should be more metal-rich than stars captured later at the outer disk. So we should expect a monotonic increase of metallicity towards the center of the resonance. Okay, so now we're going to see how the metallicity varies with vibration action. So I'm here, I've overlaid a contrast of constant vibration action and the radial action. But when we do this, we have to be very careful, because metallicity not only depends on the vibration action, but also depends on the radial action, right? The radial motion. And this is because basically stars always born at near circular orbit. And as time passes, they gain radial motions by interactions with spiral arms and giant molecular clouds and so on, which means that stars with large radial actions are on average old. And because they are old, they are also on average metal poor. And that's why we see this blue metal poor region at the rim of this velocity space. So if you want to see how the metallicity varies with these vibration actions, for example, I cannot compare stars over here and here. That wouldn't be a fair comparison. When I want to see how it depends on the vibration action, I have to look along these blue concentric rings. And it's a bit difficult to do in the velocity space. So let me just transform the coordinates. So now the x-axis is the vibration action, 0 is the resonance center, 1 is the sparatrix, and the y-axis is the radial action. So here now we can clearly see how the metallicity varies with vibration action and the radial action. Basically, the metallicity increases towards small radial action because the stars are more younger, but also towards small vibration action because they were captured earlier at the inner disk. And if I subtract the gradient in the radial actions, you can more clearly see that the metallicity is increasing towards small vibration action.
Sure, can you do similar things with the vertical action?
With the vertical
Or
actions,
like the combination of a radial and vertical action? I guess that the relation to age might be tighter.
right, yes, exactly. So yes, if I want to add in an additional dimension, I have to, again, so in this case, I have to do this with the same vertical action, or with the same vertical action, right? And in this case, I'm restricting my stars with those with very small vertical motion. So that's why I was able to do this. But if I want to, include older data with stars that have large vertical oscillations, then I have to clearly separate those samples based on what radial action they have and what vertical action they have. Okay, so here I just converted the 2D plot into 1D statistics in vibration action. So you can see that the metallicity increases towards the resonance center, and this doesn't really depend on what kind of bar amplitude I assume. And in the right plot, I'm showing the result where I apply the exact same analysis on my mock data, where the mock data created from my simulation. So the black one is the one when I assume the slowing bar, and the blue one is a constant bar. So you can see that this upward increase in metallicity is only expected when the bar is slowing down. So the fact that we do see this increase in metallicity in the data implies that the bar is slowing down. And as I explained in the beginning of the talk, this slowdown of the bar is only expected if dark matter exists.
So you would see a similar thing when the bar strength is just growing and it's not slowing down, right? Because that would also increase the trapped region.
That would increase the trapped region, but if the resonance is not moving, it will capture stars from the upper separator and the lower separator. So the actual metallicity is going to be the average between the two. So if the metallicity has like a linear gradient, then it wouldn't show any trend in metallicity. And that is exactly this case, right? So here, basically, I just I had a constant pattern speed and I just grew the bar.
So you probably expect that to be subdominant.
Yeah, so yeah, it will maybe kind of induce a fluctuation at this level.
Right, but the bar has only grown in strength by 50% over its lifetime. The width of the resonance goes like the square root of that. It's big.
So this was my chemical evidence that the bar has been slowed down. Okay, now for the analysis so far, I was assuming that the bar's pattern speed was 35, such that the corotation resonance matches the Hertz stream. And then I concluded that the bar has been slowing down, but not everyone agrees on this exact pattern speed. Okay. Everyone agrees that the pattern speed is probably around 30 to 40, but the actual exact value is still debated. So I did the analysis by kind of reversing the logic. Okay, so now I'm not going to assume anything about the bar's pattern speed, but instead I'm just going to assume that dark matter exists, and therefore the bar has been slowed down. Now, if the bar has been slowing down monotonically, then we should see a monotonic increase of metallicity towards the resonance center. So I can use this as a requirement to find the best position of the resonance and the best current bar pattern speed. So for example, if I decrease the pattern speed from 35 to 33, now we can see that the position of resonances slightly increases. And now you can see that the corotation resonance is not covering this metal-rich region properly. And if I do this trailing analysis, you see that the metallicity is undulating, which is not what we expect if the bar is monotonically slowing down. And similarly, if I increase the pattern speed to 37, now the resonance shifts downward. And now you can see that the upper separator is cutting through this metal-rich region. And again, we don't see a monotonic increase in metallicity anymore. So I did this analysis for a wide range of bar strengths and bar pattern speed. And then I quantified the likelihood of the data for each model by demanding that the metallicity increases towards the resonance center. And then again, I took the prior bar strength from a separate study, and then I estimated the optimum pattern speed to be 35.5. And then on the right, I'm kind of comparing my value with measurement from other people's studies. So this is listed in a chronological order. So the bottom ones are more recent. And I've colored it in 3. So the red data are the one that uses the local stars in the solar neighborhood, including my study. And the blue one uses the gas in the inner bar regions. the black one uses the stars in the inner bar region as well. So you can see that there was some disagreement among people, but my measurement here is generally in agreement with others. Okay, now in the second part of my talk, I would talk about, now that we have the measurement,
Sorry, I have one quick question before you moved on. Can you also put a constraint on the bar's initial rotation rate based on how large the total metallicity gradient is from center to edge of your resonance?
Okay, great, that's a good question. So basically, this gradient only contains information about the gradient of the metallicity, not the initial position. But the initial pattern speed the information for the initial pattern speed will be stored at very small vibration action, right? Because it only contributes to the part when the bar was very small. So at the current level of the data, we don't have access to those. But if we have data that directly probes the stars near the Lagrange point, we might be able to get some information about what the initial state of the bar was.
The Lagrange point is just outside of the field of view of this little guy
Exactly.
that you showed us, right? I see that.
From your simulations, can you actually tell when the bar has been formed?
When the bar has been formed. Yeah. So my simulation is a test particle simulation. It's not a superconductor simulation. So when the bar forms is something that I kind of
Right. Your simulations, I mean, you simulate in time, right? So you assume some uniform distribution and then see what happens afterward. Now we have Gaia data, so you can reverse your simulation and tell, well, when this whole thing started. That's the first question. The second question is actually, how do you know that the initial state was uniform?
So I don't assume a uniform. There is some kind of exponential profile for this. Yeah. But yes, so basically the overall result would depend not only on the evolution history of the bar, but also the evolution history of the disk, and also the current properties of the disk as well. So those are all parameters. So yes, but the thing is that for the distribution of the disk, from the simulations, we know that it has some exponential profile. So I'm following that profile. Okay, so now I will talk about, once we have the measurement of our slowing rate, what can we learn about dark matter more, not just its existence. Okay, so here I'm just showing the Affiliation motion bar. So by the way, this is just an ongoing project, so I'll just explain the basic idea of what I'm trying to do and what kind of tools that I have developed so far. So here I just want to show the concept that once we have the measurement of the bar slowing rate, by multiplying that with the bar's moment of inertia, if we knew it, we can estimate how much the torque is applied on the bar. And by subtracting the contribution from baryons, which is, again, this is not trivial, we have an estimate on how much dynamical friction is exerted on the bar. And the significant thing here is that dynamical friction not only depends on the spatial distribution of dark matter, but it also depends on the velocity distribution of dark matter. So for example, if the dark matter halo is having a net rotation in the same sense as a disk, or it might be having a counter-rotating speed. So whether the halo has a net rotation or not doesn't necessarily affect the spatial distribution of dark matter. So this is something that we cannot infer from the galactic potential. But the net rotation does significantly impact the strength of dynamic friction. So the measurement of the bar slowing rate can in principle give constraint on these kinematic parameters. So to understand, to constrain the distribution function of dark matter from dynamic friction, I first need to understand how dynamic friction depends on the distribution function. So for the rest of my talk, I'll be talking about how to model dynamical friction.
So you're assuming that the moment of inertia is constant?
Well, I mean, you can have a model for that. It depends on how the bar grows, and of course, the effective moment of inertia is not equal to the moment of inertia of the bar.
Yeah.
So you have to have a model. Okay, so dynamic friction is conventionally modeled using linear perturbation theory. So this is a formula that describes the net exchange of angular momentum between the bar and the halo. And it's based on the so-called linearized collisionless Boltzmann equation, so that's why we call it linear theory. So I first applied this conventional theory on the most simple case, where the bar is rotating at a constant pattern speed. So you can see that for the first few hundred mega years, the theory reproduces the result of simulation very nicely. But if you look into the longer timescale, in the gigayear timescale, you can see that the two disagrees badly, right? So the linear theory converges to a constant value, whereas the simulation shows this very long oscillation that bumps over time. So first I want to understand why this is the case.
How many test particles are your simulation?
So this one I use TensorFlow 9. Okay, so why did linear theory went wrong? So as I said, linear theory is based on the linearized version of Boltzmann equation. So let me just describe what that actually is. So the basic idea of linear theory is to decompose the Hamiltonian and the distribution function into an unperturbed part and a perturbed part. So in our case, H1 is the Barr's potential, and F1 is the change in the distribution of the dark matter induced by the Barr's potential. And then if you substitute this to the Boltzmann equation, which describes how the phase space density evolves over time, we get this. So basically, the Boltzmann equation tells us that the phase space density along the orbit is always conserved. This is just a Newton's theorem. But if you look at the density of a phase space at a fixed phase space, the density varies, and that variation is described by the Poisson bracket. So basically, the Poisson bracket just describes how does the function on the left evolve under the phase space flow defined by the Hamiltonian on the right. So the first part describes how does the unperturbed distribution evolve under the unperturbed Hamiltonian. And this part can be taken to be zero, right? If you assume that the unperturbed system is in a steady state. And the next term describes how does the unperturbed distribution get perturbed by the bar. So this is the linear perturbation. And then the third part describes, now once the distribution gets perturbed, how does the perturbed part evolve under the unperturbed trajectory? How does it shear along this unperturbed trajectory? This basically describes the linear phase mixing. And then the last term basically describes how does the perturbed part get further perturbed by the bar. But the gist of linear theory is basically to ignore this term. So now let's see how the phase space density actually evolves under this linearized Boltzmann equation. So initially, we have a phase space density that decreases monotonically towards larger angular momentum. Okay, so this is quite typical. And then once the bar forms, then the particles on one side of the bar will gain angular momentum, whereas particles on the other side of the bar will lose angular momentum. So some part will go up, some will go down, and then the perturbed part will now get sheared along the unperturbed trajectory, which are the horizontal. So this is how it evolves. So you can see that it's phase mixing, and you can see that the rate of phase mixing gets smaller as we come close to the resonance, and it becomes zero exactly at the resonance, because here the resonant frequency is zero. So what linear theory predicts is that after a sufficiently long time, there will be no torque from the non-resonant orbit, but only the resonant orbit will apply a torque. Okay. But we know that this is not correct. Okay, so we know that the actual phase-space flow is not like this, but it's actually like this, in a sense that the particles near the resonance get trapped and vibrate around the resonance. And recall that these orbits near the resonance conserve the fast action and the vibration action. So the right way to model the evolution of the phase space near the resonance is to change coordinate to these angular actions, right? And now because these actions are constant, now we don't have to linearize the Boltzmann equation. We can just use the non-linearized Boltzmann equation, which has a trivial solution, which basically states that the phase space density at any time can be obtained by just winding the angles backward in time. And this can be done analytically. This is how it evolves. You can see that the phase space density is evolving along these lines, right? So it's the same, it's phase mixing, but it's phase mixing in the right direction. So if I compare the result of my model with the simulation, you can see that they agree very well. Okay. So now, why does this nonlinear phase mixing cause dynamic friction? This is easily understood if you look at how the distribution in angular momentum changes with time. So here I'm just having a schematic plot for the distribution of angular momentum. So the y-axis here is now kind of converted to an x-axis here. Okay. So initially we have a negative gradient in the distribution, but this phase mixing basically works to flatten the distribution near the resonance, like this. So this means that there is a net shift of mass from the lower angular momentum side to the higher angular momentum side. And this is the reason why the halo gains net angular momentum and therefore the bar loses net angular momentum. And the physics is basically similar to Landau-Duncan if you're familiar with particle physics. So now that we know how to model the distribution function, I can compute the total torque on the halo or the bar by just multiplying it with the torque on the individual orbit and integrating over the entire phase space. So there is some integral that I have to do numerically, but if I do it, I can reproduce the oscillating behavior simulation. And then this oscillating behavior of dynamic friction is also expected in the dynamic friction on the Galactic satellite when the satellite reaches the core of the halo. This was nicely explained by Rimpei. So basically, a core means that the density is constant, and some dwarf galaxies have these constant densities. And constant density means that the potential is harmonic. So in this harmonic potential, the particles will all have the same frequencies. So what happens when the satellite sinks to this core is that they start to resonate with all the particles there. So that means that if it will initially experience a very strong friction, which is called the super Chandrasekhar friction here, because it's a friction that is stronger than the prediction by the Chandrasekhar's formula. But then as the orbit sinks, as it continues to sink, its orbital frequency doesn't change, so it continues to resonate with the same particles. So now, after some time, these resonant particles will come back to its original position. So now it will give angular momentum back to the satellite. Okay, so it will kind of go up again. And this is called dynamical buoyancy. And then if we wait for much longer time, then everything phase mixes and the satellite stops. So this is called core stop. So this mechanism was not well understood until Rimpei showed that it actually can be explained by the vibration of the trapped orbits. Now, you might have heard from Chris that in real galaxies, particles also diffuse in phase space, right? Because there's so many other perturbations like transit spiral arms, molecular clouds, and all sorts of orbiting structures. So what this diffusion does is that basically it tends to recover the original gradient in the distribution. So it kind of prevents the particles inside the resonance from completely phase mixing. And the consequence of this is that dynamic friction doesn't actually completely damp out, but it has some finite value. So this means that bars cannot keep a constant pattern spread, which is exactly what we see in the simulation as well. And this takes us to our next point, which is now how does dynamic friction work when the bar is just slowing down and the resonance is sweeping? Okay. So far I've been working on the so-called slow limit, where the pattern speed was just constant. And in this case, I've shown you that I can approximate the system with an integral system and solve the dynamics analytically. Now, in the opposite limit, which we call a fast limit, this is the limit where the bar is slowed down too rapidly, then there will be no nonlinear trapping. So actually, the linear theory works well again. And this was first described by Chiba and Weinberg. But real galaxies neither evolve in the slow limit or the fast limit. It actually evolves in this intermediate regime where we don't have an analytical solution to the equation motion. So we have to work this numerically. But I've written it as semi-numerical because even in this regime, the fast actions will be still conserved. So we don't have to solve the entire 60 phase space equation motions, but just the motion in this 2D slow angular action space. Okay, so this is how the phase space density evolves when the resonance is moving up. So you can see again that the resonance is moving, at the same time it's growing and capturing the orbit. But now we can also see that we have this phase space spiral developing as well. So when we were modeling the bar's evolutionary history, we were interested in how the property of the stars varies with distance to the resonance center. But now we are studying dynamical friction, so we are interested in how net angular momentum is transferred by this process. And basically, there are two mechanisms, right? We can classify the mechanism into two. So one is that angular momentum is transferred by the mixing, right? Both inside and outside resonances. And this causes dynamical friction. But in addition to this, when the resonance is moving, the angular momentum is directly transferred to the trapped particles because these trapped particles are dragged towards larger angular momentum. Okay. And following Chiba and Weinberg, I will call this dynamical feedback. So the exact definition of dynamical feedback in Chiba and Weinberg was a little bit different, but I will explain that in a moment. So how dynamical feedback works, yeah. First the bar slows by dynamical friction, And when it slows, it means that its rotation frequency changes, the bar's resonances move, and this is typically towards larger angular momentum. And because it moves, the trapped particles, some of them will follow the resonance and gain angular momentum. And this gain in angular momentum means that the bar have to lose additional angular momentum. And this makes the bar further slows down. So there's a kind of feedback cycle happening. That's why we call it dynamical feedback. Now, I told you that dynamical feedback is by trapped orbit, but it's actually caused by both trapped orbit and untrapped particles. And the reason is when these trapped regions move in phase space, because the phase space flow is incompressible, any particles above in the way of the moving resonance have to flow down, which means that it has to lose angular momentum. And it was actually this angular momentum, this torque due to this untrapped orbit that Schumann-Weinberg first identified and named dynamical feedback. But in my recent paper, I've shown that dynamical feedback is actually caused by both the trapped particles and the untrapped particles, and the strength is proportional to the difference between the phase space density of the trapped region and the surrounding untrapped region. So the physics is similar to buoyancy, where you want to lift a stone submerged in the water. Like if you lift it up, the water has to flow down, and so the change in the total potential energy scales with the difference between the density of the stone and the water. And they're both related because in both cases the flow is incompressible. Okay, so finally, I formulated the dynamical feedback. I wouldn't go in detail, but the basic idea is that dynamical feedback is caused purely by the movement of the resonance. So if there's any torque that arises from the mixing inside the resonance or outside, that is not feedback, that is friction, right? So to quantify dynamical feedback, I have to calculate a torque by the phase mix distribution. And at the end of the day, I get this equation, which tells us that dynamical feedback is proportional to the bar's slowing rate, and it also scales with the difference between the mass of the trapped particles and the mass of the untrapped particles displaced by the trapped volume. So this is like a phase-based analog of the Archimedes principle. So I applied this formula to the bar in the Milky Way, and I showed that around 25% of the total torque is actually from feedback, not friction. Okay, so to summarize my talk, I've shown you that the slowing bar is a unique signal for the existence of dark matter, and this cannot be explained by MOND or any other kind of modified gravity theories. And then I've shown you that the bar's evolutionary history is recorded inside resonances just like a tree ring. And then I applied this idea to the Gaia data and showed you that the metallicity increased towards the core of the bar's corotation resonance, which strongly implies that the bar has been slowing down. And then I've also explained how we can model dynamic friction in the nonlinear regime, going beyond the linear descriptions. And then finally, I would like to also mention that the bar's slowing rate, the dynamic friction by the dark matter, also depends not only on the phase space tissue, but also on the particle nature of dark matter. So for example, if dark matter is a degenerate fermion, which is forming a degenerate core in the galaxies, then dynamic friction should be weaker. And similarly, if the dark matter is a boson, and if it's in the boson and condensate, again, if the particles are having a quantum wavelength as large as a kiloparsec, then these particles will not be able to create a strong density wave, which is a small scale structure. So the friction should be weaker. Thanks for listening.
We have 2 or 3 minutes for any more questions.
So in your entire fast slow angle prescription, that is, I would say that is not entirely nonlinear, but it is a linear perturbation, or it's a second order perturbation of the Hamiltonian in the slow angle, in the slow action, right? Because you expand your h as delta js squared times something plus an angle part. So
yeah, so that is if you want to get a Hamiltonian that exactly looks like a pen, or maybe also this diagram, I expanded the Hamiltonian to second order. Taylor expanded it to Hamiltonian, so that's why it's kind of symmetric, right?
Right.
But when I did the simulation, I didn't expand. So you can see that the structure is actually symmetric.
Okay, so how much is the asymmetry? That is my question. How valid is this assumption of second order transition?
So, okay, maybe if you just look at the result here. This result is based on the second order expansion of the Hamiltonian. So yes, this is the level of precision that we can get.
It normally depends on the resonances as well. We're talking about there's certain orbits like inner limb-like resonances for nearly circular orbits where this pendulum thing breaks down completely. And I think most of the talk here is coming from corotation, for which it's pretty good. Any more? Yeah.
Yeah, so I have two questions. One is, finally, you mentioned the property of the dark matter will change the friction and the slowing down rate. Do I have any comment on fuzzy dark matter?
Right, so basically fuzzy dark matter
will make a much weaker friction.
Weaker friction, yes. Which basically I'm kind of classifying it broadly as a Bose-Einstein condensate.
Okay. And I also wonder, so you talked about the metallicity distribution when you have a bar like triangle orbit. Do you think it's possible to observe this for actual galactic sources, like for other galaxies?
Right, so for galaxies, definitely we can get the metallicity map. The thing is that the tree-ring structure is in phase space. Right.
Yes, but if you assume the JR is not so high.
Right, yes. If the orbit is mostly circular orbits, then we can do a similar thing with the real space distribution. Yes.
Okay. Has anyone done it before?
No.
One more? Yes.
Yeah, I was just wondering, you were computing the torque produced by the dark matter. How much could plausibly come from the baryons?
Right. So, for example, this dotted curve here, you can see, is a simulation where they did a bar galaxy simulation where they just frozen the dark matter. So the bar is only exchanging angular momentum with the baryons, but in a Newtonian way. And here you can see that, again, the fluctuation or the change in the bar's pattern speed is, I would say, like at most 10% level. So it's much more smaller than the friction that we expect from dark matter.
Is it obvious why it's so small?
Yeah, so I mean,
because the velocity dispersion?
No, not the velocity dispersion. I think it's just so one is just the mass ratios, but the thing is that this friction happens from a variety of resonances, and of course the corotation resonance is very close. But if you look at the resonance, the higher order resonances, they are quite far. And in those resonances, there's kind of, there's an infinite series of resonances. And for those higher order resonances, there's not much baryons there. There's only dark matter.
But the mass in baryons, the mass in the halo that can interact with the bar is about the same. And
yeah, I mean, well,
so
the thing is that when you compute the baryons, the mass of the baryons, you have to subtract the mass that the bar takes, right? And the bar is actually a very long and big structure. So the bar can only exchange momentum with the rest of the disk on outside. So that might also reduce the amount of mass that can interact with the bar.
Okay, let's continue over lunch. There will be dinner. If you'd like to sign up, please do so in the next half hour, or tell me that you'd like to come, and then I'll make a reservation. Let's thank Rimpei once again.